So, hello everyone, and thank you for joining VSA online webinar. Today, it's my great pleasure to welcome Chloé Mercier, Thierry Vieville. Is that correct? Okay. And I don't know if other two co-authors are here as well, Frédéric and Hugo. So, nevertheless, we have an exciting talk about ontology as a manifold. So without any further delay, I leave the floor to you, Chloe, and then, as I understand, so Thierry, you will take over by the end of your presentation. So please.
So thank you very much for this introduction, Evgeny, and thank you for inviting us. So my name is Chloé Mercier, and I'm working with Thierry Vieville and Frédéric Alexandre and Hugo Chateau-Laurent in the INRIA team Nemocin in Bordeaux, France. And so we are going to present you a paper called Ontology as Manifold towards Symbolic and Numeric Artificial Embedding. So this work was presented a few months ago at the workshop KRHCAI, if I got it right, which was a satellite workshop of the Knowledge Representation International Conference, focusing on hybrid systems. So to set up the context a little bit, our team, Nemocin, is especially interested in modeling human cognition and human memory. So as you may know, there are different ways to model human cognition with regard to psychology. And these kind of models will mostly be on the symbolic side. And on the biological side, now we use more and more neural networks model. Spiking neural networks are a kind of neural network that is especially biologically plausible and closer to what we think of how the neurons work in the human brain. So in order to combine these representations, we propose a geometric mapping of ontologies, which are a kind of symbolic representation, onto neuronal manifolds. So I will present a little bit some tools useful to represent ontologies, namely the Resource Description Framework, RDF, and the Web Ontology Language, OWL. And we will use those tools to map our ontology onto a neuronal manifold. So this neuronal manifold will be based on the semantic pointer architecture and the neural engineering framework developed by Chris Elliott-Smith et al. And it's itself based on the vector symbolic architecture that I guess we are all interested in. So I don't really need to present you the vector symbolic architecture, but just as a reminder, we are working with symbols encoded as vectors sampled from the unit hypersphere. And we are working in a high dimensional vector space, that is to say, two random vectors that are approximately drawn from the vector space will be approximately orthogonal. And therefore, we can use the dot product as a similarity measure in order to compare the semantic meaning of two vectors. So how do we interpret this value of the dot product? Oh, sorry, I thought that was, okay. Never mind. So why are we working in a high dimensional vector space? So as I said, we can approximate random vectors as orthogonal. And this is quite close to the neural manifold hypothesis, which, as I presented earlier, was more biologically plausible and reflects how the excitation of the spiking neurons will form a manifold in the hypersphere, in the vector space. So now let's go back to the interpretation of the dot product as a similarity measure. The most common interpretation of this number is within a closed world reasoning, so a closed world assumption. We will consider that if the dot product, the normalized dot product, is equal to 0, that means the vector are orthogonal, then we'll consider the vectors are very dissimilar from a semantic point of view. And if we get the value 1, we will consider them highly, highly similar with the same semantic content. So this, why do we interpret this as a closed world assumption? That's because in this situation, anything that cannot be stated as true is false. So anything that is not 1 is considered to be 0. That's because we were taking the normalized dot product. But if we are keeping the sign of the dot product, we end up with either -1, 0, or 1. And we could see that as an open world reasoning. So in logic, that would mean that anything might be true unless we prove it false. So some things can be merely unknown. And we will take that at the interpretation for the value of 0. 0 could be the unknown value. We don't know if those vectors have the same meaning or not. -1 would be highly dissimilar, and 1 would be highly similar, as in the previous case. And finally, we could even go even further and extend this interpretation to all values between -1 and 1, using degrees of possibility and necessity, as in the possibility theory. And so in that case, anything between 0 and 1 would be possible with a certain necessity, and anything between -1 and 0 would be not impossible, but unlikely with, in that case, again, a certain deterministic possibility. Okay, I will keep that for later, and Thierry will tell you more about it. So for now, let's go back to how we structure the universe of discourse in an ontology framework. So we consider all symbols as resources. Like in VSA, all symbols are vectors. In ontology, we'll consider all symbols as resources. These resources can be of several kinds, of several types. We can have classes. So classes are concepts. Individuals will be instances of those concepts. So individuals refer more to real world objects that can be categorized by those concepts. And finally, properties will allow us to describe the relationships between resources. So what's the syntax to write this? We will use triples, in this case weighted triples, but triples, why? Because the syntax is in the form subject, predicate, object, where subject and object are resources, and predicate is a property that will link those resources. We say weighted because we want to introduce, if needed, a certain weight tau that could account for the degree of confidence or possibility of this statement. So when we map this to the VSA, of course, the symbols that are resources will become vectors. So the subject, the predicate, and the object will all become vectors, and the tau could be a scalar. Now, how is this close to the resource description framework? So the resource description framework has the same syntax, subject, predicate, object, with triples. It doesn't have weights though, but let's stick to triples for now. And we have actually a meta model for RDF, which is called the Rdf Schema, or RDFS. So this meta model is written itself in RDF, and it describes the resources of RDF and the relationships between the different RDF entities, namely resource, class, literal, and properties. It also defines some sub-properties that I will explain a bit later. And this metamodel is useful to write lightweight ontologies. So lightweight ontologies, we mean by that by knowing the schema of the model, we can draw inferences after describing the relationships between objects. I will give an example later. So having said all this, we propose now to implement a triple store, so a store of triples, using associative memories. So let's go back to our triples. What we propose is an association between a key, which could be the subject, and a value. And in this case, it could be the predicate in the object, somehow bound together, and a scalar value. So you see where I'm going with this. Okay, let's give it another example with subject 1, predicate 1, object 1. Now, if I add another triple, subject 2, predicate 2, object 2, I will add another line in my associative memory. And let's say, for example, that I have two triples associated to the same subject as 2. I can sum up the statements associated to that subject S2 into the sum of two bound vectors, each of them weighted. So we see now that we need to introduce a scalar multiplication, a vector superposition, so the sum here, and a vector binding, so there's B that I did not detail yet. And this is very close to the semantic pointer architecture proposed by Elias-Smith. In that case, we will use binding, which was developed by Gosman and Elias-Smith, which is called the vector-derived transformation binding. The particularity of this binding is that it is not commutative and not associative, although it is distributive and bilinear, and it admits right identity and right inverses. So why do we need this non-commutativity? Okay, I will get back to it. So now the associative memory that I proposed earlier, it was also implemented in the neural engineering framework, which was also developed by Elias-Smith in the context of the semantic pointer architecture. And so these associative memories can be actually simulated in Nengo, which is a simulator for the neural engineering framework. So we can use associative memories between spiking neural networks to implement this kind of things. Okay, I will, for now, I will forget about the top, so you can see that I removed them. Okay, let's do an example because maybe it's a bit abstract for now. I will give an example of a very, very small ontology about pizzas, which was inspired by the famous tutorial about pizzas developed by Stanford and Manchester. So let's pretend that we have a pizza and Luigi is eating the pizza. Luigi is an instance of person. Person is a class. And this pizza is an instance of Margherita pizza, which is also a class. Margherita pizza is also a subclass of the class pizza. We would like to perform inferences on that using a rule called the inheritance inference rule. And this rule states that if we have an instant X of a class C, and we have a class C that is itself a subclass of the class C prime, then X is also an instance of C prime. In that case, we can add a relationship type between this pizza and pizza. So we can infer that this pizza is an instance of the class pizza. And this is the kind of reasoning that we would like machines to perform automatically just by using vector calculations. So how do we achieve that? If we use the binding notations that I used earlier, using the binding matrix of the vector-derived transformation binding, we can see that we just need to replace the product, the matrix product of B type and B subclass by B type. This will simplify the two relationships here into just one. The problem is that in associative memories, we cannot store matrix. We can only store vectors. But that's actually okay, because we will introduce an operator which accounts, so this operator is between two vectors, and when applied to two vectors, the binding matrix associated to this operator becomes the product, the matrix product of the two binding matrices. So this will help us store the inference rules that I defined here into in the form of vectors into the associative memories. So this is an operator which is always defined because of the definition of the vector binding vector derived from transformation binding at the definition of the binding matrix, which is block diagonal. Now let's give an implementation, a concrete implementation of that using for example, Nengo. So first we start with a Q, which is the subject of interest. In our case, this pizza. This is the subject that we want to infer things on. We retrieve this pizza from a first associative memory. And this first associative memory stored the facts, the things that we already know about the pizza. So in that case, we retrieve the relationship between margarita and type. So we understand that this pizza is of type margarita pizza. And then, so we unbind this margarita from this result given by the associative matrix. And we, and we bind it to a second Q type. We unbind it from the second Q type, which is our predicate of interest. So type is the predicate that we want to infer something about the type of this pizza. So now that we have unbound this margarita, we will again look up into the associative memory, and we will find the binding of pizza and subclass of. So this relationship tells us that margarita is a subclass of pizza. We will store that for now and bind it, and we will bind it to our first Q of predicate of interest. So we end up with this. And finally, we have a third Q, which is the rule to apply. So you can think of this as a question answering. So in that case, the question is about the type of this pizza. And the rule to apply, we could actually look up all the rules, all the possible rules that are stored in the associative memory. And we will find the rule that is relevant to be applied on so that we can infer what we wanted to infer. So the rule to apply is this, the binding of the new operator. I don't really have a name for it, between type and subclass of. And by looking up in the associative memory too, the one that stored the rules, we will find type, which is our simplification. And by binding this time, this type to the pizza here, and this pizza comes from the unbinding of BB pizza subclass of type and type subclass of, we will find the inferred statement B pizza type. So we can conclude that this pizza is of type pizza. I'm really sorry. I don't know if that was all clear because it's kind of a long example to explain. Is it okay?
Yeah, sure.
So let's move on. I drew a few plots. So you can see here the numbers. They will actually refer to the signals of the vectors of the neurons in Nengo. So here are the plots. You can see here that the first one which was the Q of interest, shows that it's a very high similarity when we compare it to the other words of the vocabulary. It's very similar to this pizza, so we can deduce that this is the right subject Q, this pizza, and this is how the neural network will process the Q and understand it. Then same goes with the predicate Q, which is type, and with the rule Q, which is type combined with subclass of. Now the outcomes of the network are the numbers 4, 5, 6. So here are the outcomes. The outcomes 4 shows that the inferred object is indeed pizza, and the plot 5 shows that the inferred predicate is indeed type. And finally, the inferred statement, we can deduce that this pizza is of type pizza. So that was the example. I didn't really get into the details of the underlying mathematics of the vector-derived transformation binding. So we can go a little bit more further. So this was the vector-derived transformation binding that I did not really detail, but you can see here that the binding matrix is block diagonal, and this is why we can define this operator that I defined earlier in order to transform the product of the binding matrices into combination of two vectors. Now, the unbinding, I didn't really go into the details either, but this operation admits right approximate inverses. And these approximate inverses are actually quite easy to find. We just need to permute the element of a vector to get the right approximate inverse. Since it admits right approximate inverses, it also admits a right identity vector. So this right identity vector is such that when you bind it on the left to the identity matrix, you will get the vector again. And the binding matrix associated to this right identity vector is the identity matrix. So yeah, we already understood that, but that means that we can check if a property is a predicate for a given resource, because the predicate will be the vector that will help us construct the binding matrix. And checking then if the result belongs to the vocabulary by using the similarity measures that I defined earlier using the dot product. So you might wonder, can we do it the other way around? Like I showed an example where I have the subject and the predicate, and I want to infer the object. Now what happens if I have the subject and an object and I want to infer the predicate, the relationship that links them? This is actually also possible because we have a very convenient matrix, which we will call B with arrows, like this. And this matrix can flip the order of the operands. So that means that if we have a subject and null object and we want to infer the predicate between them, we can use this matrix to flip the order of the operand and perform the same kind of inferences that we did earlier. So this is just the mathematical proof that this operator exists. And it's also interesting because it's computable in O of D. I don't know how to say that in English. I'm really sorry, but it's computable like this. So yeah. Okay. These are just small examples of inference rules that we could use to make some inferences. Now, what happens if we want to infer more things? So use more inference rules. This is what we are going to discuss now. So we only see the type inheritance inference on the first example. but there are actually a lot more RDFS entailments available. For example, we could infer a property. If a property is the subproperty of another property, then we can infer that any resources linked by this property will be also linked, by the subproperty, then they will also be linked by the property. We can also infer on the range and the domain. So the range and the domain of a property is the values that this property can take and can be applied to. So for example, the domain of a property is the class of all the resources that this property can be applied to on, and the range is the values that the property can take. So the class of the values that the property can take. So if we know the range of a property, automatically, if we know that a subject is linked to an object through this property, then we can, by knowing the range or the domain, we can infer the classes of the subject and the object. Beyond our DFS, we also have other kinds of inferences. For example, in OWL, so this language that I didn't present yet, but I mentioned earlier, the web ontology language. This is based on description logics, and it provides even more inferences. And for even more reasoning power, we could even combine it to swirl rules, which are other kinds of inference rules that are expressed directly. I will show an example later. And so we were wondering if we could also implement these kinds of inferences using our formalism. So we will, this will be maybe kind of an informal presentation now, where we will submit some ideas to you, and we can discuss all together. You can stop me at any point. These are the RDFS entailments. I will not present all of them to you because that's not very interesting, but so the one that we addressed was the second one right now. And we are interested in addressing basically all the other ones, but especially the ones on domain and range and the property propagation. So type inheritance, we have already done that. Substantion transitivity, we didn't address that one, but this is actually achievable also on with the same mechanisms that we presented earlier. So substantion transitivity, this is hard to say, consists in this relationship subclass of, which is transitive. So for example, if Margherita pizza is a subclass of pizza and pizza is itself a subclass of food, then by knowing that this pizza is of type Margherita pizza, we can infer that this pizza is also a type food, because Margherita pizza will be a subclass of food by transitivity of the subsumption relationship, sorry. So in this case, the rule that will be stored in the associative memory that stores the rules, as presented earlier, will be this. So subclass of combined with subclass of can be substituted by just one subclass of. Now, what happens with domain and range inferences? This one is a little bit different. So in this case, we will introduce something a bit original. So an unknown vector, which we can call epsilon, for example. And this vector actually accounts for the open world assumption. That means that if we know the domain of a property, for example, we know that the resources that this property is applied to are in this domain. But we don't necessarily know what resources this property is applied to. Because since we're in an open world assumption, we might not know everything, and we might not know what resources are in the domain. So this is why we introduce this vector. This vector means that there is a resource in the domain that this property is applied to. It says that it exists without specifying which one. So this is actually very useful to implement this kind of inferences, either on domain or ranges. The same goes with range inferences. So this is what we would store in the associative memory 1, the one about the facts, and in the associative memory 2, the one about the rules. In the one about the facts, you can see this epsilon vector. And if we don't want to use the epsilon vector, because sometimes it could happen that for some reason you don't want to consider the unknown objects that are in the statement, you can just project on the orthogonal of this vector to get rid of it somehow, and only retrieve the known vectors. So yeah, this is how it could be achieved, but we haven't really tested it yet. Yes, property propagation. Okay, this one is a bit tricky. So property propagation, as I said, is when a property is a sub-property of another property. And using the mechanisms that we defined, we realized that this kind of inference was only possible when the vector accounting for sub-property of was the identity vector, which is maybe, we don't really know yet if it's a problem or not. So we were thinking maybe if we substitute all the is-a relationships, like subclass of or type and subproperty of, obviously, with the identity vector, since we don't have an equal sign between the subject and the object predicate pair, I mean, why not? It's just an association, but we don't know yet if this is sound. Maybe it could lead to weird inferences. So this is still an ongoing work, and we would also be happy to have your feedback on this. And at least they are property composition. So this one is not actually an RDFS entailment rule. It's although it's a rule that is present in OWL, in the second version of OWL 2. So it's similar to OWL property chains. But this one says that we can chain properties. Like, for example, if you are eating a pizza that has a certain topping, you are also eating that topping. So you can chain relationships like this and simplify them into just one. So this mechanism is exactly the same as the one in the ones for the inheritance inference rule. So this works too. Yeah, I didn't really explain what OWL was about. But as I said, OWL is based on description logics, which is a fragment of first order logic. And this is why it would be interesting for us to also implement OWL inferences, because since it's based on description logic, it has more reasoning capabilities, and under some certain constraints. So in the case of the profile that is called OWL-DL, because OWL has several profiles, but in some of the profiles you would have computability and decidability under some constraints. So this would be also interesting from a computational point of view and computability point of view. In OWL, this is a little bit different because in most profiles, except for one, individual and classes are really disjoint sets. You cannot treat a class as an individual, whereas in RDF and RDFS, nothing really prevents it. So this is one of the differences between the two. It's a bit more constrained. And Swirl, also the weird tool that I mentioned. So it's a language that allows to add some rules in the form of implications, such as, for example, if you have a parent which has a brother, you have an uncle. So This example might not be the best because it's very similar to property chains, but you can also have some rules that are really not achievable with just OWL itself. So, or at least not very easily achievable without a lot of verbosity. So we could present an alternate implementation. Thierry, maybe you want to step up about that?
With pleasure, under your control.
Sure.
So here it's more a speculative part of the talk. Now I know the English word. The idea is to show that there is a lot of potential. And in particular, on the next slide, there are alternate, if you don't mind, there are alternate implementation of the different rules we were talking about. So we have to understand something. You have some triplets, some facts, and you have some rules that allow you to derive other triplets. And with this segment of logic, the idea is to compute the closure, which means that is to compute all the possible triplets that you can have, either offline and then you look if the triplet exists, or online. And of course, you ask for a triplet and the system turns the wheel and there it finds the right, if the triplet is there or not, sorry. Which means that, I'm still on this slide, which means that we have to be able to enumerate, given a rule and given a set of triplets, all the triplets on which the rule may happen. If we can do this, we have the basic tool to generate the triplets we want in either offline or online manner. And what you have in front of you is an alternate representation where we put all triplets in a given box. So we every subject, property, object is added, and is added thanks to binding operation. You have the binding operation in front of you. So they are all, because random high dimensional vector, they are all more or less orthogonal. So we can pick in this data structure what we need. And thanks to the algebra that you present, Chloé, in particular, I need to stay.
Still not. Still
in particular, this operator, which is the O/ operator that you designed, by the way, Chloé. Thanks to this O/ operator, we are able to really extract from this triplet box all the triplets we need. And yes, I agree, we can go on the next slide. So here we have the enumeration of all the mechanic we need to extract the different triplets. And the message on this rather complicated things is that we can enumerate all combination we want. On the next slide.
Yeah, just to complete, the idea here is that you can see that in the compressed triple store, you have a products of bound matrices, and this is very hard to retrieve and very costly from a computational point of view from at a first thought. But thanks to this possibility of indexing triples either by subject, property, or object, you bypass this kind of computational difficulty.
Absolutely. So here we took again the class inheritance example. So, you know, if something is of a given, a type means class in this context. So if something is of a given class and the class is a subclass, etc., then you can deduce this transitive rule in a sense. If you write the algorithmic mechanism that compute the closure, you obtain this not so complicated, but quite heavy algorithm. And up to my best knowledge, we need to compute this algorithm. We don't have simpler algorithms to compute to implement this class inheritance rule. Let's see now what happens with our numerical implementation. With the numerical implementation, we can transform this mechanism to a simple operator where you have two triplets and you have some, you can calculate if they are equal, etc. And this is a kind of TOR1 operation, of unique operation. And if you look carefully, we also can introduce in computation a kind of lambda between 0, 1, a kind of operator. If you are not sure whether it's false or true, unknown or true, sorry, then you have a kind of, you can have a proportion of trueness or belief, to be clear, that can be introduced in calculation. And in the next slide, okay. And in the next slide, we were going to, yeah, I was expecting something, so go back. And thanks to this, now we have a rather simple mechanism. You have a network where you put all the triplet box. You have this numerical operator that loop, that feedback on the box. And after a certain number of loops, you compute the closure, the fixed point, and you compute what you were expecting, which is all triplets that you can deduce from a given set of facts. Great. Another point where we are thinking about is a representation of belief. So Chloé explained us very clearly that in a closed world, it's between false and true. In an open world, it's between false unknown in the middle or true, which is related to something called the clean logic. If we go a step further, on the next slide, there is a notion of possibility and necessity. And this is a very nice mechanism where you can claim that something is possible, which means it's not false in a sense, or that something is necessary. And in front of you, there is a formalism that allows us to represent belief which seems to be closer to the way the brain represents belief. So, I'm sorry. Our contribution to this is that in the vanilla theory, in the basic theory, as soon as the possibility is, the possibility is below 1, so if something is not fully possible, it cannot be necessary. And on the reverse, as soon as something is a bit necessary, so necessity is higher than 0, it must be fully possible. This can be understood if you are in a deterministic world. But if you are in a stochastic world, it appears to us that this notion has to be generalized a bit. And as you can read in the first line, here we try, using, for instance, things derived from Dempfner theory and so on, we try to say, okay, necessity and possibility could be bounds, could be an interval of the unknown probability. So understand that we are in a world where, on one hand, we can be sure that something is random, like throwing a coin, and we know the probability, half and half. Or we can be in a situation where we have only partial knowledge about the probability. We even don't know what is this. We know the system is a bit random or a lot random, and we don't know what is the probability. This is exactly what we want to represent here. If we go to the next slide. So thanks to students of Chloé and I, he has been able to relate in a rather proper way, as you can read on this slide, this notion of probability and the notion of necessity and possibility, because there are a set of property of coherence property that have to be verified. And so the idea is that the person has a set of knowledge, and given the set of knowledge and an observation, is observe something, he can output a belief, which means he can say, okay, I can estimate the necessity of this event E or the possibility of this event E. The technical work here was to be sure that it was compatible and was to see how we must adjust the numbers in order the probability axiom, because this has to be coherent with probability. So we have to respect some probability axiom. So the work here was to be sure that everything was coherent. On the next slide, we are going to skip, skip this. I only say one word. We also check that this is coherent with a Boolean reasoning, because as you can imagine, there are false and true value, and we of course want that the usual logic to be not broken by this mechanism. Go to the next slide. Now comes the VSA implementation. Okay, guys. Now we want to implement in VSA not only one number between -1 and 1, but two numbers. In fact, one number between -1 and 1, false from true and unknown, and another number, which is the second dimension, the length of the vector in the second dimension, and which correspond to the level of randomness. So how can we do? And here we observe two things. On one hand, all what we have developed, guys, with VSA, including the VTB binding operation, seems to pretty nicely work with complex numbers. So if you just said, okay, now it's not a real numbers, but a complex number, we can reuse all your stuff. And that was good news. However, we also ask ourselves, well, do we gain something to use complex numbers, or do we simply can use pair of real numbers? In other words, do we need something specific to the complex field? And the answer is open, and actually we are not very convinced that it's using explicitly the complex field is an add-on, that we benefit from something, but it's still possible. Next slide, which I think, yeah. On the conclusion, maybe you can say a few words on the conclusion.
Sure. So just to sum up a little bit what we have presented. So what we propose is, I believe, an original way of combining ontologies and VSAs, providing a distributive approach and a very tight coupling between symbolic and numeric approaches. This also, so this comes from an inspiration from both biology and psychologically, since we are mostly interested in modeling human cognition. Something that we didn't say, by the way, about the proposition of a compressed triple store is that it comes from a discussion with Terry Stewart, who is also part of Chris Elias-Smith's lab. And he said it was quite biologically plausible to imagine that when you want to avoid retrieval in associative memories, which can be also a bit costly, it's like a retrieval in a semantic memory or in the long-term memory, you might want to keep the retrieved information, so the retrieved triples, into just one vector. So this compressed vector that we presented afterwards could be our working memory kind of way to keep the bindings in one simple place. So that was just a parenthesis on biologically plausible approaches. So the first approach that we presented involved two associative memories, one to store the statements, the ontological facts, and another one to store the inference rules that we could then apply to the facts to infer new facts. Using this, we achieved several kinds of inferences among the RDFS entailments, namely concept inclusion and inheritance, so the subsumption transitivity and the inheritance of class. We also managed to implement domains and ranges, but we are not sure that we have, for example, the subproperty propagation thing. This is still an ongoing work. And we are also wondering if we could extend this to owl ontologies. Some thoughts on that we didn't really mention either, but maybe the class complement, for example, could come quite straightforwardly by the opposite of a vector. But that's also something that we need to discuss. So finally, scalability and completeness and soundness, these are also ongoing studies. We have only tested our mechanisms on a very small ontology. So maybe now the challenge is also to see if that would work with a bigger ontologies with a large vocabulary. So this is also a perspective of this work. Another problem is that these mechanisms don't really learn from the inferences because we are not yet able to update the associative memory in a spiking neural network kind of way to add the infer relationships. But this is also I think this is an ongoing work on the side of Elias Smith lab. But yeah, this is also something that we follow closely so that we can use it if it becomes available. And yeah, I didn't conclude on the possibility and necessity theory perspectives, but it would be also interesting to see how we can model the degrees of belief and degrees of possibility and necessity in those facts by weighing the triples or adding this this scopal necessity probability. This this number.
Here we are.
All right. Thank you very much for your talk.
Thank you.
So now we up for questions.
Yeah, I had a question. Can you hear me?
Yes, Tony, please.
Yeah. Chloé, really interesting stuff you did with all the RDF entailments. I was wondering how much work you think you can make the dot product value do. So if you flip back to your slide 25, what I'm thinking about is like the type hierarchy has quite a few levels, and can you have something, like your margarita pizza, is a baked dish, is food, is a thing. Can you capture the sort of the levels of that hierarchy with different dot products, or do you need some other way of capturing that? And when I was looking at this here, I was saying, okay, it looks like the margarita pizza is really high, but everything else seemed really low and possibly not very distinguishable.
Yes. So it's a very interesting question. It comes down to the scalability of our model, because the more vectors we have, the less likely we are to draw them orthogonally. So if we have too many vectors, and if the dimension of the space is not high enough, we might end up with vectors that won't be orthogonal. And that could be a problem because we may not be able to discern them, distinguish them from another when we compute the similarity. So sorry.
Yeah, sorry. Finish what you were saying. I just had a follow up.
No, I just wanted to conclude.
Yeah. Okay.
It's the dimension of the vector and the size of the vocabulary. That's
right. Okay. So what dimensionality vectors did you use here for these experiments?
So in this case, it was already quite high. It was of the order of the hundreds. Thierry, I don't know if you remember the exact number. I have it in the paper, but no.
I'm back in a second with the answer.
Okay, right, but it was hundreds, not thousands.
Around 100, and the vocabulary is quite small here.
Yes,
so
right. Okay, yeah.
How many dimensions?
Yeah, sure. Yeah, I know. When I was trying experiments to try and get at these kind of questions and finding I needed sort of 5,000 dimensional vectors to get good separation, and which was a little bit concerning that the dimensionality was so high. But okay, thank you.
You're welcome.
More questions? We still have time for some more questions.
We do have questions for the community. For instance, one question is, has any of us been interested in studying complex VSA representation, and for which need? That's a kind of question we have, and we need help and advice about this.
Yeah, so this is Fritz. We actually look quite a bit into the complex VSAs in our work, which is the reason we were interested in these is that we are looking into also spiking implementations of, and basically the spikes represent the phases of a phase or of a complex number. And so yeah, I can point you to some papers.
Yes, very interesting.
I have a question on my own. What about related concepts? So now you presented a case where all your categories, they are distinct symbols. So you encode them with orthogonal vectors. But I guess in general, you might have a case where there is a similarity between concepts, right? How would this be addressed?
This is
maybe
yeah,
I
this
give,
is not.
please.
Sorry. No, yes, indeed, the paradigm that we have here is that all symbols are orthogonal, which is quite something strong to ask. But I don't know, in other VSA applications, what happens if two concepts are very similar? Is there a way to still be able to distinguish them somehow?
That's a good question. Well, actually, you're right that there are not that many examples where people, a case with similar concepts is considered, but yeah, I don't know how to answer your question directly.
But this is definitely a limitation.
No, obviously it's a limitation if you want to retrieve it accurately.
So could I jump in with a speculation for an answer there? Which is that if you were to raise the objects to a higher power, they would become more orthogonal. So if you had some way to construct this as a recurrent circuit so that the representations were raised to powers of themselves over time, they would become more orthogonal over time as well, because the dot product is you're raising the dot products to a higher power, so being less than one, of course they get smaller. That's completely speculative and possibly of no use whatsoever.
Oh, that's interesting.
It's very interesting, and in a more confused way, in a sense. We had the same question. At the beginning, we thought that with VSA, we were allowed to change the value of the random orthogonal vectors. And people said, no, you draw your vector at the beginning, thanks to the numerical properties, they are almost orthogonal. And then if you want to add some information, you bind, you use binding. If you think about other numerical symbolic representation, their representation, they allowed to change the value, for instance, turtle and turquoise. Turquoise, you can say in English, yeah? which are two words for tortue in French. So they are close, so you just draw them randomly, and then you are more or less allowed to make them similar, which means that you are allowed to change the value. And so for us, it's an open question. I'm just adding a question on your question. Very interesting.
Well, there is also, of course, the semantic pointers and the fractional power encoding. So there are extensions to VSAs where you can deal with actually things that are not, that should not be orthogonal, but should have systematically a higher inner product. And so there's recent papers, several, you know, but it's basically fractional power encoding. I mean, actually, Tony Blade's old idea to use, for example, you know, a seed vector, a complex valued phasor vector, and then you actually just use this exponentiation that also Ross just mentioned to basically encode numbers. And now if the exponents are very similar, then of course the vectors are very similar and they have higher inner product. And as you move away with the exponent from the other exponent, they become more and more orthogonal.
Ah, very interesting. We knew, Chloé, the fact that you can encode numbers by power mechanics, if I may summarize that way.
Yeah.
But,
it's called, I think Tony Blade invented it, right, and called it the fractional power vector, I think. And we wrote recently a paper where we show how actually VSAs connect also to kernel methods. And there we call it fractional power encoding. The Elias-Smith group, for some reason, calls these things semantic pointers, but it's all the same thing.
Yeah. So one thing that stopped us, in a sense, is what we knew about this. The binding operation was convolution. However, as Chloé explained, we need a non-commutative convolution, like VTB or what you want.
Actually, maybe sorry, Thierry, maybe I didn't make this very clear why, but this is very simply not to confuse the object with the predicate, because it could lead to very confusing inferences. And I don't think I mentioned that, so
oh yes,
my bad. But yeah.
Yeah, thank you for this precision. So we have not been able to make the synthesis between this power, including fractional power mechanism, using, up to my best knowledge, convolutional binding, and our need to have non-commutative binding operation. So still an open question for us.
I have a couple of comments related to orthogonality, and that's if you really get your dimensionality into the thousands, then you get a huge number of approximately orthogonal vectors, and so if you are in it's like 100 or 200 or 300, you don't get that advantage yet. And the other thing is how about related concepts, and here are related to some experiments we've been doing, and that is classification or identification. And if you try to like identify speakers, that's one project I've been working on with another person. All the speakers are highly correlated. If you think of each speaker as a concept, you really are dealing with very highly correlated concepts. But yet, we can linearly separate most of the speakers from the rest of them. So, and that's means that you're dealing with very highly correlated concepts, and high dimensionality lets you separate one from another, quite high probability. And the other thing is that you almost have to be able to stand high correlations, because, well, you want to say, okay, this is speech, and in order to recognize it's a speech, it has to be correlated with other speech. Whereas, okay, this is music, so it has to be recognized as music. It has to be correlated with other music. So I don't think we'll really ever get away from correlated concepts. So that's sort of what I've learned in trying to do classification. So that's, I don't know if that helps answer your question, but I think it comes to the point of, you know, is each person, each speaker a concept, is each piece of music a concept or not? So.
Very interesting and very inspiring. Sorry, thank you.
Maybe another question from my side, or maybe you have commented it somehow during the talk and I missed it. But I mean, with VSA, we always talk about this kind of bridging capability between connectionists and symbolic AI, even in terms of symbol grounding. I mean, for the symbolic part. So how is this symbol grounding happening here in your approach? So the symbols are, so you I mean, I understand the descriptive part. So you have an ontology, you have symbols, you encode them, but the grounding.
We don't really address the question of the grounding here. And this is also because our system doesn't really learn, but it performs reasoning. It performs
sure. Mm-hmm.
That's indeed the concepts are fed to the network, so it doesn't ground the concept itself. Indeed.
Yeah, and maybe kind of. I mean, when I was asking about related concepts, I maybe meant that sometimes while symbols could be orthogonal, during the grounding, the concepts could appear very near each other, but consistently near. So if for example, I did an experiment, which I reported in one of in my last talk. So when you, for example, learn, languages based on texts, like 20 in an unsupervised way, and then you see that. So obviously the texts they're very close to each other. I mean, cosine close, like Dutch and Swedish and Danish. So they're very close, closer than French, for example. But and they're consistently close. But then what I mean with my question is rather, I mean, probably you need yet another associative memory where you map this consistently close concept to more orthogonal symbols which you assign, and then and in this way you would do the grounding maybe.
That's a very, very interesting point. Yes, I don't know what you think, Thierry, but indeed adding this kind of layer of grounding to what we were doing on reasoning on symbols would be.
Yes, it's it's a very good question, and at the beginning I need to ask which grounding. I have a kind of low-level definition of grounding, which is there is a symbolic operation that can be realized numerically.
Mm-hmm. And that's what you do actually here, right?
Absolutely. So let's call that small grounding.
Yeah, sure. Absolutely.
And then there is, we know, the symbol grounding problem, where we have a system that for which words get sense, if I may use a Franglish. And frankly speaking, we are not able to address at this level the big grounding problem. We only are happy to have solved in our context and in our case the small grounding problem, where of course if two concepts are similar, so we are not able to make them numerically similar, so to make that the dot product, whatever it is higher than 0, but we are able to add new properties to say that these two concepts are similar. For instance, in all, there is something who can say that a turtle and a tortoise, it's the same thing, in fact. So to put sense on the symbol, we have to use additional triples, additional elements to put in the ontology. I'm not very proud of my answer, but this is my best frank answer around regarding this huge grounding problem.
Yeah.
Okay, thank you.
In our case, concept similarity is mostly addressed by the associative memory itself, which relates similar concept to another. But yeah, that's another layer, I would say, indeed.
So let me ask once again if there are any last minute questions from the audience. Ross, please.
Sorry, I was actually waiting for Pentti to mention this, and I'm going to do it severe injustice. Thierry and Chloé, you were talking of the turtle tortoise example, and how initially you'd start with vectors for turtle and tortoise drawn at random, so they're effectively orthogonal. And how do you learn? Pentti did some work called random indexing some while back, which is about learning patterns in words, but I think the same thing applies here, that essentially, and Pentti, I hope you'll correct me if I'm getting this completely wrong, that they would start off, all the items they were representing had two components to them. One which was essentially the name or an identity, so turtle or tortoise, but the other part, and that was fixed throughout the life of the system. But then bound to that would be an accumulation of values associated with it. So the values you associate that get picked up with, so effectively the grounding of turtle and the grounding of tortoise, end up being empirically very similar. So then, you know, you've still got the bindings are orthogonal because turtle and tortoise are orthogonal, but if you can query it with the properties, what you get back is a mixture of turtle and tortoise. Pentti, have I completely murdered that?
No, you're doing fine. You're doing fine. No, the thing is what seems to me that what language gives us, it gives us very easily, it gives us nearly orthogonal labels. Words are just random labels. And if they were not, then we'd all speak the same language. But, you know, so you start with random labels, and then you see these labels in different contexts. And by using random labels, then you can compute new vectors that somehow reflect similarity between words. That particular random indexing, it was sort of done as an alternative to latent semantic analysis, which is computationally pretty heavy. It requires singular value decomposition. And it's very hard to do if your vocabulary, like in the case of language, vocabulary gets into like hundreds of thousands of words. So what the random indexing lets you do, it lets you deal with large vocabularies, large set of things. And the large means that for each of those things, there is a random label, and in a high dimensional space, you really don't run out of approximate orthogonal labels. That's sort of a lesson from that particular exercise.
Yes. All right. So it feels like we had a great discussion. So and this is thanks to our speakers today. So Chloé and Thierry. So thank you very much for joining us. And well, we have our mailing list for further discussions and individual lists. So well, we'll keep in touch. So exciting work. Thank you very much, and thank you all for joining. So we see each other in 2 weeks. So on the next webinar. So goodbye for now.
Bye-bye.
Thank you.
Bye.
Thank you.